is a very important concept in biochemistry, which is why we kind of like jump in right in the beginning with all that math. It's not because we're trying to be mean, it's just that understanding pH and the relationship between pH and whether things are protonated or not, whether there's free protons hanging around to catalyze reactions. All of this is really important, and to know all of this, we need to basically know these equations, know how we can do things like figure out what the pH of a solution would be if you were to dissolve a weak acid or a weak base, do things like figure out how we can control the pH by making buffers that have almost equal amounts of conjugate acid and conjugate base, so there's enough base there to mop up any acid and enough acid there to mop up any base. To do things like predict how the pH would actually change if you were to add a strong acid or a strong base to that buffer you made. It can also allow you to do things like predict whether reactions are going to go faster or slower if they rely on having a certain amount of protons around. So there are lots of different reasons why pH comes into play, and there are a bunch of different types of calculations that we can do to figure out various things about the pH. So here are some work through examples for these. Start off with an overview of the different types, and then I will break up the rest of the video into smaller parts as well and post those individually. So if you want to jump just to one certain question type, you can go ahead and do that. But let's just dive in. The best way to learn acid and base equations is really just to practice them, but it can help to have some examples and a kind of overview as to the types of problems that you might be encountering and strategies for approaching each of them. Then you can go ahead and try a bunch of practice problems, and don't worry, you'll get a lot of practice in class. So let's go over the four kind of main types of problems, and then I'll go through how we can think about each type. The first type is going to be the simplest. And in this type, what you have is you have some sort of acid, and you're going to dissolve it in a solution. And when you dissolve it in a solution, some of it's going to dissociate. So some of it is going to deprotonate. And then you're going to be able to calculate what proportion deprotonated, what's the concentration of the deprotonated versus and the concentration of the protonated form, so the conjugate base and the conjugate acid, and what's the pH of the resulting solution. You'll also be able to do problems where instead of just dissolving your acid in water, you're actually mixing it with the base and then seeing what happens. Now you could be asked things like, what's the concentration of each of those acids and bases, both their conjugate acid form and the conjugate base, as well as what's the pH of the solution. So an important point that we're going to be coming back to over and over is that we have an equation called the pKa that's going to tell us about the strength of an acid, and that's going to be a constant. So our pKa is not going to change, but the pH of the solution can change depending on the concentration of our acids and of our bases. And so we'll see how that's going to affect things, how that can be altered in different conditions. Speaking of altering that pH, so remember that the pH is going to be dependent on the proton concentration from all sources. So this is the source of the acid that you dissolved. In the simplest case, the only source of the protons is going to be from that acid you dissolved. But in other cases, you can have acid from multiple acids going on. And especially one thing that we often do in the lab is we take a solution and we are going to adjust the pH of that solution. Or maybe in your bodies, you have a molecule and like an amino acid, and you want to figure out, okay, well, what proportion of it is protonated or deprotonated? But that amino acid isn't just the only thing in that solution. Instead, there's lots of other things. There's lots of other acids that are contributing protons. And so the pH is going to be different. But using this equation, this Henderson-Hasselbalch equation, you'll be able to calculate the proportion that is protonated or deprotonated. And if you know volumes and stuff, you can calculate the actual moles, the quantities. In the lab, what we're going to be doing, and you'll get lots of practice of this buffer calculations in the lab, is basically you want to make a pH buffer. So basically a combination of a weak acid and its conjugate base that is designed, like you titrate it, basically you want to get it at the concentration of your acid and your base where it's at a pH that you want it to be at. So remember that the pH is going to be dependent on the amount of the proton availability. Now we'll see in the first type of problem that if we just dissolve an acid in water, we're going to reach some sort of equilibrium and we're going to have a specific pH, and that pH is going to depend on the concentration of that acid or of the acid that we add, as well as the pKa of that acid. Those are going to determine what the pH is going to be. But that doesn't mean that we're stuck at that pH. So we'll have some initial values, some initial ratio of products of our acid and our base. But then if we, and we'll have some initial concentration, therefore, of our protons and therefore our pH. But if we add an external acid or a base, then we can shift that pH. And then if we shift the pH, well, now we are going to change our concentrations of our acid and our base, and then we can calculate that as well. These are going to be more complicated calculations, and so we're going to use this thing called an ICE table. Some of you might be familiar with an ICE table, maybe from your general chemistry class. But basically what you do is you take your initial concentrations, then you take the change into concentrations, and then you use that to calculate the difference at equilibrium. And so we're going to be stressing this point a lot. Equilibrium. When we talk about our Ka, in our pKa, this is going to be at equilibrium. So basically, you would dissolve your acid in water, you let it mix, and then eventually it's going to reach an equilibrium, and that's where you want to calculate things. Now, initially, say you add an acid or you add a base or something like this, when you have this change, you're perturbing the system. So you might have some initial equilibrium in the case of those hardest problems, or you're just going to be dissolving something in the case of the easiest problems. But you can think of having some sort of equilibrium or some sort of initial conditions. And then you're going to perturb that and then reach a new equilibrium. And when you reach this equilibrium, this is when you're then going to take into account your Ka, because that's an equilibrium constant. For any reaction that's at equilibrium, we can write an equilibrium constant that's going to be equal to the concentration of our products over the concentration of our reactants. And instead of just simply adding together if you have multiple products, instead of just adding them together, you're actually going to be multiplying them. And same with reactants. So, and if you had stoichiometric coefficients, you'd be raising them to the coefficient. So go ahead and review your chemistry book and notes and all that good stuff to refresh your memory of these equilibrium constants. But you can do this for any sort of reaction, including the dissociation of an acid. And so when we do this for the dissociation of an acid, then we call it our Ka. So our Ka is going to be equal to the concentration of our conjugate base times the concentration of protons divided by the concentration of our acid. And we typically abbreviate this generic acid HA and its conjugate base A-. And then we can write this as H+, or what I typically do is I like to write it as H3O+, because what happens is that we're having this happen in an aqueous solution. So we're going to ignore the actual water because it's such a high concentration. We can consider that it's not changing. But we do want to consider the fact that we have all the protons, and the protons, instead of just hanging around freely, they're going to be latching on to a water molecule. And so we get this hydronium ion, but you might see it written. So you'll see it either written as a hydronium ion or just as a proton H+. Now, so this would be the Ka, but typically what you're actually going to be seeing is the pKa. And so the pKa is the negative log of the Ka. It's similar to how the pH is going to be the negative log of the hydronium concentration or of your proton concentration. So that little p just indicates you're taking the negative log. Now, with mathematical rearrangement, if you have the pKa, you can calculate the Ka, and if you have the Ka, you can calculate the pKa. So if you need to calculate the Ka, because you're typically given the pKa, that's going to be what can be measured and what you can find in like a table, say. You can get those for different acids, and the stronger the acid, the lower the pKa is going to be. because that's going to mean that it has a higher Ka. So more dissociation, higher Ka, and therefore, because of this inverse relationship, it's going to be a lower pKa. And so another way to think about this is the pKa is going to be the concentration at which the pH at which half of it is protonated and half of it is deprotonated. If you have a lower pKa, that's going to mean that you need to get to a lower pH. You need to get to more extreme conditions in order for half of it to still be protonated. And so under typical conditions, most of it is going to be deprotonated. And so we'll get into examples of all of this. But basically, if you're above the pKa, then you're more than half of it is going to be in the deprotonated state, because remember, that's higher pH, lower H+ concentration. So there's lower protons around to pick up, and therefore you're less likely to be protonated. And the lower the pKa, the less likely you are to kind of take one of those protons and hold on to it if you run into it. So we'll see much more examples of this throughout the course. So that was the Ka and the pKa in the pH. And you can actually combine all three of these, and we'll see that we can do this using something called the Henderson-Hasselbalch equation. So we're going to use this whenever we're perturbing the system. So we're going to use this whenever we're perturbing a system with extra acid or base. So basically, you don't just have that one thing in there. You're going to adjust the pH with something else. So you're kind of adjusting, maybe in the lab, you're adding an acid or a base, or in your body, you have a solution already at a certain pH, and then you want to say, okay, well, this component within it, what is the proportion of it that's protonated or deprotonated, given that it's in this environment at a certain pH. And so those are going to be the cases in which we'll be using the Henderson-Hasselbalch equation. And we'll look at an example of how we can do that. And then we'll be going over some ways in which we can use this to, say, figure out what proportion of an amino acid is protonated or deprotonated at a given pH, given its pKa. So we'll be doing lots of that. And then finally, there's this equation that we're going to use when we're mixing an acid and a base that can come in really handy. Basically, it just comes from rearranging all this stuff. And you can figure out that KEQ is also equal to 10 to the power of the pKa of your products minus the pKa of your reactants. And so we'll get an example of that in a minute.